Okay, willing participants, we are going to jump into chapter 13. We're looking at chemical kinetics. So this is all about kind of how particles are moving and how this really looks at how fast reactions will happen. So before we jump into this, I want to do a little bit of background information looking at the kind of baseline factors that will affect the chemical reaction rate. Now, because what we're dealing with is bonds breaking and bonds forming, reaction speed depends upon the nature of the bonds and the reactants themselves. And there's four factors that will allow us to change the rate at which any given reaction will occur. One will be the physical state of the reactants, one will be the concentration of the reactants, one will be the temperature of the reaction, and one will be the presence of a catalyst. And this is what we'll look at throughout this chapter. This is again kind of an overview. So looking at the physical state of the reactants, so one of the basic rules of a reaction is that the reactants must physically collide, must physically come together in order to react. And the easier they can collide, the more rapidly they can react. And so if you think about physical states of matter, certain physical states of matter allow for easier collisions. Because when reactants are in different phases, different states of matter, the reaction is limited to their area of contact. So for instance, if you have one that's a liquid and one that's a solid, the liquid has, like, things can move throughout the liquid, but the solid, only the very surface of the solid can actually come in contact with something else. So that will kind of limit that area of contact. The general rule is more surface area means faster reaction because there's more that's available. And we generally see this if we take a solid and the finer we powder it, the greater the surface area becomes. Next will be concentration. So again, concentration goes up, reaction rate goes up. Should make sense because higher concentration, more of the chemicals that are present, and so more collisions can occur. Blah, 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 what I said. Temperature. The rates of chemical reactions increases with temperature. In most cases, and we'll talk more about this when we get into the next unit, but and the reason that this is happening, like we talked about the gases, at higher temperatures, the particles are moving faster. As they're moving faster, they're going to collide with each other more frequently. And because there's more frequent collisions, it works. The reverse is also why we refrigerate food. We make it colder to slow the particles down. As we slow the particles down, there's less collisions and slower reaction rates. And finally, a catalyst. So this chapter, we're actually going to get into kind of exactly what catalysts do, but they will increase the reaction rate, but they're not used up. And we'll see kind of how this works again as this chapter progresses. They actually affect how the molecules themselves collide. They provide for easier, better routes of the chemical reaction. So again, overall, reaction rate is all based upon this frequency of collisions. The greater the frequency, the greater the rate of reaction. But there's this other piece. For a collision to lead to a reaction, the collision must happen with enough energy. It's not enough just to collide, they have to collide energetically enough. Because what happens is that energy is being used to stretch those original bonds to a critical length so they can kind of snap and reform. And they have to have the right orientation for new bonds to form in the right location. So you can almost think of this like if you're working on a car and you want to change what's on there. And if you want to change a tire, you can't just hit the hood of the car with your hands. You have to have the right connection in the right place. So now we're going to look at section 13.2, looking at what it means when we talk about the rate of a chemical reaction. In simple terms, we're really talking how fast is the reaction. But it's not enough to just say it's fast, it's slow. We can actually calculate what that rate is. So again, think about like your car. In your car doesn't just have two gauges. It's not just your car is going fast or your car is going slow. It has a speedometer telling you exactly how, well, roughly how fast you're going. Very similar with reaction rate. We want a number to it. At the heart of it, it's a rate. And rates are always a change in amount in some amount of time. And that's what this is as well. We're looking at the change in concentration, usually reactants, but we can view it from products as well. The change in the concentration of reactants per some amount of time. If it's a fast reaction, we might be seconds. If it's a long reaction, it could be decades. But that's just part of the unit. So usually it will be molarity per second because we're looking at the change in the concentration. So again, molarity per second. Now, we can view this as either the rate of the disappearance of reactant A, because A is getting used up, or the appearance of product B. So the average rate of appearance B, chemical B, over a time interval is given by the change in concentration divided by the time change. So again, you could look at how reactant B increases, what its molarity changes, divide that by the time change, and you have your. So let's say we wanted to look at the average reaction rate of a reaction like this. So we can see the concentration is going down. It starts at 0.1 and it ends at 0.02. So this would likely be a reactant because we see that concentration going down. So if I wanted to find the average reaction rate here, I could take my end molarity, so ignore that, 0.02, subtract the initial, 0.1, and it took place over 800 seconds. Sorry for the penmanship, I'm drawing this with a mouse on my computer. And when I do this, I get negative 0.98 molarity over 800 seconds. And if I use my trusty calculator, that tells me a reaction rate, average reaction rate of negative 0.00123 molarity per second. So that would be the average reaction rate. Notice that negative there. Generally, when we talk reaction rates, by default, we don't have any negatives. So we would say that this has a reaction rate of 0.00123 molarity per second, acknowledging that we're finding this from the concentration change of a reactant. That's where the negative comes in. And we'll talk more about the fine details of this as we proceed. Now, why would we graph this? Well, because we've graphed it, we could actually find what's called the instantaneous rate. Because notice in that last one I talked average rate. Well, instantaneous rate ends up being a much more useful piece of information because instantaneous rate is the rate at any particular moment in the reaction. Not overall, just any moment, because reactions will speed up, they'll slow down. Usually they slow down as they proceed. And to do this, we find this from the slope or the tangent of this curve at any point in interest, and we'll talk about what that means on the next slide. If you're in calculus already, you know what this means, so just hum along, imagine a cat in your mind or something, just play along. So, if we can find the slope of our line at any point, that will give us the instantaneous rate of that reaction. So here I have kind of two examples. So I have this reaction here, hydrogen plus iodine gives me that hydrogen monoxide. The red curve starting here is the rate of appearance of HI. The green curve starting here is the disappearance of hydrogen. And what we see is we can find the instantaneous rate. So we pick this point in time, so roughly 50 seconds. And what you do is you take a straight edge and you lay it along your graph so that at the point of interest, it looks like it's making a straight line. It's kind of, you're pretending that that curve is a straight line at a little point. And you match it up as best you can. And then you draw that straight line. That's what's called your tangent line. Once you have your tangent line, you can then find the slope, rise over run. You can see that they did that up here. So we kind of picked this point. They just kind of laid a straight edge along and tried to match up with the slope of that line right at that point. And then they can find the tangent line, rise over run, giving the rate. So a little bit of calculus insert. If you're not in calculus, just ignore this. Technically, the reaction rate is the first derivative of concentration with respect to time. You will never, if you're not in calculus, you don't have to know what that means for the AP test. But if you want to sound fancy, and if your parent asks you, "Dear son or daughter, what did you learn in school today?" You can say, "I learned that reaction rate is the first derivative of concentration with respect to time," and they will think you're very smart and likely buy you a car. So if I was to do this in calculus, this is how it would look. You would put the reaction concentration of what you're looking at there. But again, if you're not in calculus, don't worry about it. Now in the future, when I say rate, we're going to be talking instantaneous rate unless told otherwise. And a lot of what this chapter is finding different ways of finding that instantaneous rate. Doing it graphically with the tangent lines is tedious. But you will have homework questions where you have to do that, FYI. The rate at reaction time 0, we're going to call initial rate. We're going to be doing a lot of stuff with the initial rate of a reaction. Now stoichiometry plays in as well. If everything in the reaction, your reactants and products, exist in a 1-to-1 ratio, then the rate of the disappearance of A would be the same as the rate of the appearance of B. Again, that's assuming a 1-to-1 ratio. But as we know, not all stoichiometry has coefficients of 1. That would make balancing equations very simple. So how do we deal with situations that are not 1-to-1? Like this reaction. This is the decomposition of the same reaction we saw in the graph earlier. We can measure the rate either in terms of the disappearance here of the HI, which has the coefficient of 2, or the rate of the appearance of either of the products. But if I want a reaction rate, we need to have this normalized. We want one reaction rate for all of this. So how do we do that? Well, what we have to take into consideration is this coefficient business. Because that HI has the coefficient of 2, there's going to be 2 moles of HI disappearing for every mole of hydrogen or iodine that is produced. It'll actually disappear twice as fast. So to normalize this, all we do is we take the rate of the disappearance of HI and divide it by its coefficient. We divide it by 2. If it had a coefficient of 5, we would take its rate, divide it by 5. Whatever the coefficients are, that's what we divide the rate of the appearance or disappearance of that by to get the reaction rate for the overall problem. Okay, so now we're getting into 13.3. This is a long section, just as an FYI. So the big thing we're looking at here is something called the rate law. And what the rate law allows you to do, it looks at the relationship mathematically between concentration and reaction rate, and will allow you given concentration to actually calculate what the reaction rate will be when those concentrations are true. So oftentimes it's initial reaction rate is very, very common. And that's what this talks about. So how do we do this? We do this by creating a rate law. And a rate law, again, shows how the rate of the reaction depends upon the concentration of the reactant. So again, that initial concentration piece. So if you have a general reaction that looks like this, the uppercase letters would be some chemical, the lowercase letters would be your coefficients. The rate law looks like this. One thing I want to point out right away, so there's no confusion about this, is notice the coefficients are not in the equation at all. They don't matter. I want to make this explicitly clear. The reaction rate has nothing to do with the coefficients of your balanced equation. We're going to have rate is equal to chemical 1, chemical 2, these would both be reactants, some exponent I'll talk about in a moment, another exponent I'll talk about, and that K, which will be a constant because chemists can't spell. So I like to use K's for constant. It's called the rate constant. And the rate constant is a numeric value. It has a unit, we'll talk about that in a bit, that depends on the reaction itself and temperature. Different temperatures for the same reaction actually shift the rate constant. The exponents are generally small whole numbers, 0, 1, or 2. I say generally. On the AP test, they will be 0, 1, or 2. Now, if you're looking at this in college or something outside of AP chemistry, it is possible to have larger exponents. It is possible to have fractional exponents. It is even possible to have negative exponents. We are not dealing with those because those are not on the AP test. Now, once you have the rate law itself, so the exponent piece, and the value of the rate constant, you can then find the rate of that reaction for any given set of concentrations of the reactants. You just plug them in. But the big thing is those exponents. How do we find the exponents? Because I want to be very clear, they are not the coefficients in your balanced equation. So again, we know the general form. The exponents are called reaction orders. So in this case, we could say the order, reaction order, or just the order with respect to A, or the order with respect to B. So let's say we have a reaction. It has ammonium, it has nitrite. This is its rate law. Let's just make one up. Let's say this is a rate law. This is a perfectly fine rate law. Because we don't see an exponent, what exponent does that imply? That's right, willing participants. That means it's a 1. So we would say that that reaction is first order with respect to ammonium, also first order with respect to nitrite. Now, you not only have order with respect to each reactant, but you also have overall order. Now, if n is equal to 0, and I'll get back to that overall order in a moment. So if n is equal to 0, we say that that reaction is 0 order with respect to that chemical. That actually means that that chemical does not impact rate at all. If n is 1, we say it's first order. And if it's first order, that means the rate is directly proportional to the concentration of A, which means if we double the concentration of A, we actually double the rate of the reaction. If we half the concentration of A, we half the order of the reaction. Finally, if n is equal to 2, we say it's second order, and that means the rate is proportional to the square of the concentration. So if we doubled the concentration of A in a second order reaction, that would be second order, so doubled would be 2. 2 squared is 4. If we tripled the concentration, that would be 3. 3 squared is 9, so it'd actually be 9 times rate. Now I mentioned there's an overall reaction order as well. The overall reaction order is the sum of the individual orders. So with this rate law that we saw before, again that right here, each thing here has a kind of hidden reaction order of 1, and 1 plus 1 is 2, so the overall reaction order would be 2. So it'd be second order overall reaction. Now, how do we find those exponents? If we can't get them from the coefficients in the balanced equation, where do they come from? It has to come from experimental data, period, with a small asterisk for a subnote, which I'll get to later. But experimental data. Again, usually the rate orders will be 0, 1, or 2. And we kind of keep that in mind when we start analyzing data. And I'll have an example coming up in a moment. And again, we could have negative, we could have fractional, but we won't. For AP chemistry, there should not be negative reaction orders. There should not be fractional reaction orders. It's not in the AP test. Don't worry about it. Last thing I want to talk about before we get to how to find and actually finding those reaction orders is the units of the rate constant. And the AP people love to ask this question. They'll often ask you to find the value of the rate constant, and we'll see how to do that, and also what its unit is. And here's the deal. The unit on the rate constant is whatever it has to be to make the units work. And I know that's vague. Here's the deal. We know that its rate equals the rate constant K times some molarities to some power. But one side of the equation where it says rate is molarity per second. That is set. So the rate constant has whatever units it has to in order to make it so that the right side of the equation is also molarity per second. So here's an example. We have a generic second order reaction. So it's second order overall, and it's second order with respect to A. Now, viewing this, what I like to do once I have my kind of equation set up, I write down the units that we see. Rate, again, is molarity per second. There's our K, and it's molarity because it's concentration, and the squared because of the squared. That's where everything comes from. Now again, the left side is and will always be molarity per second. So K is whatever it has to be to make the right side molarity per second. So I'm kind of putting in just an X, a generic thing there, a placeholder. And I ask myself, what does X have to be if this is molarity squared? So I often view it like this. So I kind of, there's where X would be, and then molarity squared. Again, drawing with the mouse, I apologize. Well, looking at it, I see that there's no seconds here on the right. And I need seconds on the bottom because rate is molarity per second. So at the very least, there's going to be seconds down on the bottom. Now here it's molarity squared, and by here I mean here, molarity squared. We don't want molarity squared, we just want molarity. We want molarity per second. So I need to cancel out one of the molarities. So I put a molarity on the bottom. That's a times. So now we'll see that one molarity cancels, the square cancels, leaving us with a molarity on top seconds on the bottom, giving us molarity per second. So that would be the unit of the K, because that's what it had to be to make the right side of the equation molarity per second. So how do we use these initial rates to determine those rate laws? Well, again, you need experimental data. And what we do is we change the initial concentrations of the reactants experimentally and record what that does to the rate. So we're going to work through an example. But first I'll give you the rules. So here's the deal. If a reaction order is 0, that means changing its concentration does not change the rate. We still need some of that reactant present, but as long as there's more than 0, doesn't affect the rate. So if we like doubled the concentration of A and it didn't change the rate, A would be 0 order. If it's first order, that means the change in concentration produces a proportional change in the rate. So if I tripled the concentration of A, I'd see a tripling of the rate. If I half the concentration of A, I'd see half the rate. And again, if it's second order, it means it's changing by a rate of the square of the change. So if I tripled the concentration of A, that's a 3 times multiplier. 3 squared is 9. I should see 9 times the rate. Now again, rate depends on concentration. The rate constant does not. The rate constant is based upon temperature and the reaction. As long as we're not changing that, the rate constant stays the same. So here's our example. This is our reaction. We are told, here's a reaction. And then the initial rate is going to be shown on the next slide. And we want to find the rate law and the rate constant, including units. This is not an uncommon problem to see in AP chemistry. So this is what we see. So we have on the here concentrations of NO2, different trials. So trial 1, 2, 3, and 4. I see concentrations of CO during those trials, and I see the rates. Very important. Now, the way we're going to do this is we're going to look for 2 runs of data where one reactant is kept constant and the other is changed, so we can isolate what's happening to the one that is changed. So looking at this here, I notice that between runs 1 and 2, the NO is changed, but the CO remains the same. So that's good to look for the NO. Likewise, I can see runs 2 and 3. The NO remains the same, and the CO changes. So that'd be good, 2 good runs to look at to determine the order of the CO. So when I compare runs 1 and 2, I see that the NO2 concentration is doubled, but again, the CO stayed the same. So I then look at the reaction rate. If by doubling the concentration of NO, the rate stayed the same, then it'd be 0 order. Because I doubled the concentration, if the rate doubled, that'd be first order. If by doubling the concentration, the rate quadrupled, that would be second order. And what we can see is that that quadrupled the rate. So that would be, so again, we went from 0.0021 to 0.0082. Personally, what I like to do, I just grab my calculator and divide the 2, just to see what that multiplier is. And again, we know that, we know that. So because it had a 4 times increase with a doubling of NO2, that tells me we would expect second order. So the NO2's exponent is second order. Comparing runs 2 and 3, we saw that we doubled the CO. NO2 stayed the same. And if I look at this, so again, with these 2 runs here, by doubling the CO, there is no appreciable difference in the rate. So what order would that be? That would be zero order. So the overall rate law would look like this. Now before you panic, what happened to CO? Well, remember that if something is raised to the power of 0, the whole thing has a value of 1. We don't have to include it. You could write, and it would be absolutely correct, you could do that as well. You could put some brackets, put CO, bracket, and 0. That would also be 100% correct, but you don't have to. You don't have to do that. So we're not going to. So that's the overall rate law. Now, let's see it there. We want to find the rate constant. So to do that, now that we have the rate law, this is easy. We just pick one run of data. So again, we could pick run 1, run 2, run 3, run 4. It doesn't matter. And we simply plug it into the equation. I am efficient, not lazy. I am efficient. And so the way I always approach this is I always pick run number 1, if it looks good, and just plug it in. So we know the rate. We know the NO2. And we know the CO, not that it matters because it's raised to the power of 0. You just plug it in and solve for K. And you get your rate constant. So that is the value with unit. If you're curious about how I found that unit, again, we can view that through, we know that rate is molarity per second. We know that K is whatever it has to be, so let's kind of leave a blank there. We know that because of the NO2 squared, that is molarity squared. So again, we ask ourselves, what has to be inside those brackets, the parentheses, to make the right equal to molarity per second? Well, at the very least, I need a per second, so I add a per second. I also have to get rid of one of the molarities because this is molarity squared, right there. So now molarity per 1 over molarity per second, which is what we see here, just written in fancy notation. So we're going to look at section 13.4. This is called the integrated rate law. So it's still a rate law, but where the rate law is all about what is the rate given the concentrations, the integrated rate law is what is the rate given concentration at a specific point in time. So rate law is all about that initial rate. Integrated rate law is about the rate with initial concentrations, but at a specific point in time. Now to do this, we have to actually convert our prior rate laws into a new equation, and this requires calculus. I do not expect you to use calculus. The College Board does not expect you to use calculus. But we can use the equations that calculus would give us. In fact, in your equation packet are the integrated rate laws. You just need to know how to use them, not how to create them. So we're going to start easy with a first order reaction. Now again, we know a first order reaction, it depends upon the concentration of a single reactant raised to the first power. So we see something like this: rate is equal to rate constant times concentration of some reactant. Now we calculasize. By the way, if you're in calculus, I strongly recommend yelling calculasize before you do any calculus every single time. Your teacher will not get annoyed with it at all, I promise. For those of you who are in calculus, we're going to integrate. That's why it's called the integrated rate law. If you have no idea what that means, don't worry. And what we do is we do some math and we end up with this equation here. Don't worry where this comes from. This is also where it is. Don't worry where this comes from. Again, this is, I believe, what is in the equation packet itself. I'll talk about the equation in a moment. This is called the integrated rate law. ln means natural log. You're not really, you're just using your calculator. Use your calculator. Hit the natural log button. K is still your rate constant, and now T is at some point in time. So A sub O would be your initial concentration. A sub T would be your new concentration. So you could do a few different things with this. You could be asked to say, so the initial concentration is 5 molar. After 30 seconds, so 5 molar would go there. After 30 seconds, so time would go there. What's the new concentration? So then you solve for that. That is absolutely something you could do. You could also kind of do it backwards. You could say, okay, here's the rate constant, which maybe you found earlier. We have some initial concentration. Now we have this concentration. How much time has passed? So it's always going to be solving really for one of those three variables usually. Now, we can also write it like this. And I like to write it like this. Why do I like to write it like this? Well, I'll tell you in a moment. By the way, any of these, all of these equations can be used with any concentrations unit as long as you're consistent, but you're generally going to see molarity. So back to that. So we can actually use this equation to verify that a reaction is first order. How do we do that? We graph it. This equation is actually the slope-intercept equation in disguise. So slope-intercept is y equals mx plus b. This is y. Negative k is m, t is x, and the natural log of a sub o is b. And so what we see, if we actually graph on a graph, instead of just y values, but if we actually graph the natural log of the concentration on the y-axis and time on the x, and if it's first order, we get a straight line. Notice that we should expect a negative slope because of that negative right there. If it's not first order and you try to do this, won't be a straight line. It's as simple as that. Now, as a few notes, when we are dealing with gases, we can substitute pressure for concentration. The units end up working out the same. And again, if we graph our data, the slope of the line becomes the negative k. This is another way to find a rate constant, by the way, is just find the slope of the line, slap a negative sign in front of it, which actually makes the value positive because it'll always be a negative slope, and then you can get your k value from there. Now, second order, we do very similar things. So we can either have some reactant going to products if it's second order with respect to A, or A plus B goes to products if A and B are both first order. We're going to go simple. So here's a nice second order reaction. This is the integrated rate law. It's what it is. Don't ask me how. It's calculus. Ask your calculus teacher. Yes, I can do calculus. I just don't want to in this video. This also is in the form of the slope-intercept. Here is y. K is m. T is x. And b is 1 over the initial concentration. So we can also find if a reaction is second order is we graph it. If when you graph it, and by the way, when I say graph it, that means they're going to do 1 over the concentration at different points in time versus time. And if that makes a straight line, then that is second order. So you often have to do both. If you graph the natural log versus time, and it's straight, it's first order. If you graph the reciprocal of concentration over time, if that's straight, it's second order. Now, a very common AP question is it'll ask you to evaluate purely based on the graph if their order is first, zero, or second order. So again, you look at the three graphs. If it's zero order, so it would be zero order if just concentration versus time is straight. If the natural log of concentration versus time is straight, that's first order. And if the reciprocal of concentration versus time is straight, that makes it second order. Again, whichever gives the straightest line is the correct one. Now this brings us to this idea of half-life. The half-life is the amount of time required for the initial concentration to reach half of its value. So if you started with a concentration of 10, however long it would take to get to a concentration of 5 would be a half-life. And half-life is a nice way to describe how fast a reaction occurs. We often hear about half-life in terms of nuclear decay, but it can also be described in terms of medicine, how long it's effective. If a half-life has if a certain medicine has a half-life of 12 hours, that means the initial dose that you took, half of its concentration is gone 12 hours later. Now, again, we usually do this with first order reactions, but not always. We'll talk about why in a moment. Now, a fast reaction will have a short half-life. A slow reaction will have a long half-life. So here's an example, half-life for a first order reaction. So at time 0, we see we have a concentration of 1. At time 100, we see we have a concentration of 0.5. We went from 100 to 0.5, that's half the concentration, so that means 100 seconds was our half-life. So from 0.5 to 0.25, so that's half concentration, 200 seconds. So again, we see a time of 100 seconds is our half-life. And this is what we see again after 3 half-lives. From 0.25 to 0.125 is we have another half-life, another 100 seconds, still another half-life. Every amount of time it gets to half the concentration is a half-life. First order reactions actually have a consistent half-life. We can find the half-life of a reaction by substituting half the concentration into the integrated rate law. So for a first order reaction, this is getting really messy. So again, we'd have the initial concentration, half of the initial concentration, concentration cancels out, so natural log of 1/2 gives us a constant. So this is actually the equation, the half-life for a first order reaction is always going to be 0.693 over K. K again being our rate constant. We can see from that for a first order reaction, half-life is independent of concentration. It's just 0.693 over K. So we will see for a first order reaction, half-life is constant. Also, by the way, a way of finding if a reaction is first order. So if we had some reactant with a concentration of 0.120, after one half-life, it would have a concentration of 0.060, half concentration. After another half-life, 0.03, I forgot the 0 there, sorry. What about second order reactions? Well, things become muddier, and you get this equation. Notice here that concentration now plays a role. And because concentration is on the bottom, the larger the concentration, that means the smaller the half-life. So the reaction is going to be substantially faster. The half-life is actually smaller at higher concentrations. So we learned in the introduction that there is this relationship between temperature and reaction rate, where generally higher temperature means faster reaction rate. But what this section is all about is kind of the explanation of why and a little bit of a deeper dive into that. And so again, we know rates of most reactions goes up as temperature goes up. What this means is as temperature increases, that means the rate constant generally increases. Because if you remember the rate law, rate equals that K times whatever. This is affecting the K. That's how to deal with this, we're going to look at what we call the collision model. Now the collision model is based primarily upon kinetic molecular theory, which is good because we discussed that back in chapter 5. Now, what's going to be nice about this is it's going to allow us to relate the reaction rate to both concentration and temperature, which is one of our goals. Now, the basic rule of the collision model is that molecules must actually collide with each other in order to react. The more collisions we can get per second, the greater the reaction rate. And so we know that as concentration increases, that means we're going to have more collisions, thus increasing the reaction rate. So again, if we think back to in chapter 5, I introduced the idea of the freshman testing facility. If you have a bunch of blindfolded freshmen wandering around a room, the more freshmen you have in there, the more they're going to collide. Very simple. Now, what we also know is that according to the kinetic molecular theory, as molecules move faster, that means they're colliding more forcefully with more energy and more frequently. So again, both increasing reaction rate. But one thing we want to be aware of is that for a reaction to occur, we require more than just the collision. In fact, only a tiny fraction of the collisions that occur lead to an actual chemical reaction. So why is that? Something's keeping those reactions from happening more rapidly. And this brings us to what we call the orientation factor. And what this says in broad scope is that molecules must be oriented in a certain direction for the reaction to occur when they collide. And what this means is that these relative orientations to each other determines if the molecules, if the atoms are positioned to form those new bonds, to break the right bonds to form the new bonds. They have to be in the right place. So a lot of reactions don't occur because the molecules just aren't facing the right way. To put this into some slightly lewd terminology is think in broad strokes of a male and a female trying to have a baby. There's an orientation factor at play. If there weren't an orientation factor at play, crowded hallways would be a much more hazardous environment than maybe they already are. But there is definitely an orientation factor. Similarly with molecules. So that just shows here. So like that first one, it starred. Yay, it's a star. It's a star because that's the right orientation. And B, it's not the right orientation. Boo, boo, wrong orientation. Because there's also activation energy. So activation energy was figured out in 1888 by a Swedish chemist named Svante Arrhenius. And he hypothesized that molecules must have a certain minimum amount of energy in order to react with each other. Now, we know from the collision model, this energy itself comes from the kinetic energy of the colliding molecules. They have to be moving fast enough. They have to have enough kinetic energy. Now, upon that collision, the kinetic energy of the molecules can be used to stretch, bend, even break chemical bonds, allowing us to have the chemical reaction that we need. But if the molecules are moving too slowly with not enough energy, they'll just bounce off of each other without reacting. Think of it like bumper cars. Bumper cars move at a slow speed. They can collide with each other without permanently deforming. If they're moving fast enough, that's not the same. So in order to react, the colliding molecules must have some total kinetic energy equal to or greater than some minimum. We call that minimum amount of energy the activation energy, or E sub A. And this varies from reaction to reaction. It depends on the chemicals. Again, what we generally would expect is the more stable the molecules, the higher its activation energy should be. And kind of a golf analogy, so think about a golfer putting. There's a hill over the green that the putter must get over. The putter must give the ball enough kinetic energy to get it at least to the top of the hill for it to have any chance of making it to the green. If there isn't enough energy, the ball rolls partway up, then back down. So we see something like this. We have a certain amount of energy for our reactants, certain amount of energy for our products, and then we have to give it a certain amount of energy. They have to have energy. From the reactants to the highest point, that is your activation energy amount. If you can meet the activation energy requirement, then the molecules can make it over through the transition state, that kind of in-between point, and then once they can have enough energy, when they fall apart, they will fall apart into the products that we know and love and want. Now, when you look at energy diagrams like that, again, the activation energy is that amount of energy needed to force the molecule through that intermediate state to get to the final product. In other words, the intermediate state is during the collision itself. And the intermediate state is very unstable. It's going to fall apart. What it falls apart into depends upon the activation energy, if you have enough energy to meet that amount. If you do, it'll fall apart into the products. If you don't, it'll fall apart back into the reactants. So yeah, and we talked about that. Now, exothermic or endothermic. So the reaction we saw like earlier was exothermic. How do we know? Because the product had less energy than the reactants. That's as simple as it is. If the products have more energy, then it's endothermic. This is generally how an endothermic reaction looks. Here at the left, we have our reactants. Here at the right, we have our products. And we can see that the products are higher in energy than the reactants. That means endothermic. In reverse, so this is the difference. So, this is even doing a little fun thing. This would be exothermic. Now, energy and rate. Energy change, total energy change, exothermic or endothermic, has no effect on the rate of the reaction, but rate does depend upon the activation energy itself. Generally, the lower the activation energy is, the faster the reaction. Think of it like a cost. If something costs a small amount of money, it sells faster. Same basic idea. More molecules will have the necessary energy to meet that requirement, and the reaction can proceed. Now, how do molecules get their energy? They get their energy by collisions. Again, when molecules collide with each other, they can transfer energy between themselves. So as they collide, molecules gain, molecules lose, and what we see is at lower temperatures, less molecules will have enough energy to overcome the energy barriers. It doesn't mean no will. Through sheer dumb luck, certain molecules may have enough energy to meet that activation energy requirement and can react, but it's going to be very, very small amounts. At higher temperatures, more molecules have enough kinetic energy, so we're going to see more molecules reacting. Note, as activation energy increases, K should decrease. Again, K being that rate constant, the higher the rate constant, the higher the rate. Higher rate means lower activation energy. So to rate this from slowest to fastest, we have two graphs here. And again, it's all about the activation energy, not what they're labeling as C here. C would be the total energy change between, that's endothermic or exothermic, one on the left being exothermic, one on the right being endothermic. That has nothing to do with rate. The speed is all about this activation energy. All about this activation energy. Higher activation energy should be the slowest. Slower activation energy should be lowest activation energy would be the slowest. And we are into the home stretch here. We're doing 13.6. This is the last section in the chapter. So we know that a balanced equation shows us what substances we start with and what we end with. That's it. But it doesn't tell us how the reaction occurs. And I want to be clear about that. It's just saying what we start and what we end, not with the middle. The process by which a reaction occurs is called the reaction mechanism. And that's different. Now, a good reaction mechanism should show us everything. Should show us what bonds are breaking, should show transition states, should show catalysts, shows us everything we need to know. And that's what we're going to look at, is what those reaction mechanisms are. Now, the heart of reaction mechanisms are what we call elementary reactions. So let's say this reaction here. Let's just say that is an elementary reaction. By the way, do not assume a reaction is elementary unless you are told so. I am saying, let's say this is an elementary reaction. Elementary reactions occur in a single step or event. What you see is the reaction. So if I say that the elementary reaction is this, that means one molecule of NO reacts with one molecule of ozone to form one molecule of NO2 and one molecule of oxygen. That's it. Now, however many molecules are in the reactants defines what is called molecularity. If there is a single one molecule involved in the reactants, we say that the reaction is unimolecular. If the elementary reaction involves two reactant molecules, that could be two different molecules or perhaps two of the same molecules, just two molecules in general, we would say that's bimolecular. If an elementary reaction involves three molecules, and what this is meaning is that three molecules have to simultaneously collide with each other in the right orientation, we call those termolecular. They're not very probable, not very often. Again, you have to have three molecules colliding in just the right way at the same time. Now, if we look at a balanced equation, it is the overall picture of the reaction. But most overall reactions occur through a multi-step mechanism. This means a sequence of elementary reactions. As a note, in AP Chemistry, you will never have to generate a multi-step mechanism. One will be provided for you. You may have to analyze one, but you will never have to produce one. So here's a reaction. Now we say below most temperatures, this reaction occurs in two elementary steps. Those are the two. So the first one is two molecules of NO2 colliding, producing NO3 and NO. And then we take that NO3 from the first step, react it with carbon monoxide, and we get NO2 and CO2. That is what we're saying. That's the steps. In a chemical equation, if you add together all of the elementary steps, canceling out things that appear on opposite sides, so if a molecule appears on the reactants in one step and the products in another, they cancel out. But one way you check your mechanism is that your individual steps have to add up to the overall balanced chemical equation. So if I add those two steps together, I get this, just adding up all the reactants, adding up all the products, which gives us the original equation. Because I can see here, like I have an NO3 and an NO3, so they cancel. I have an NO2, and that means I can cancel one of those NO2s, leaving me with the original equation from above. Now, because we see here this NO3 is neither a reactant nor a product in the original, that means it's what we call an intermediate. Intermediates are formed in an early step and consumed in a later step. All multi-step mechanisms involve one or more intermediates. We never see intermediates in the end chemical equation. So here's an example. Conversion of ozone into oxygen proceeds by a two-step mechanism. So first is that, then that. Those are the two steps we are proposing. We're going to do three things. We're going to describe the molecularity of each elementary step. We're going to write the equation for the overall reaction and identify the intermediates. So, same steps there. So the top equation, molecularity, because I see one reactant, that means it is unimolecular. The second reaction, because I see two molecules, would be bimolecular. Now the overall equation, so now I can start canceling stuff out. So I see in the first step, oxygen is produced. In the second step, oxygen is used. So that oxygen atom is canceled out. So that's not part of the overall equation. And also notice I have an oxygen in the products and two oxygens in the products. So that gives us an overall of 3. Also, there's 2 ozones, hence 2 ozones. Now the intermediate is what was produced, that means a product in an early step, and used, that means a reactant in a later step. That would be the oxygen atom. Got canceled out. We cancel out the intermediates. Now we can write rate laws for elementary reactions, and I want to be very clear about this. Earlier on, I told you you cannot use a balanced equation to write a rate law. That is true. You can use elementary reactions. Now the reason we can't use the balanced equation is because the overall equation is made up of those multiple elementary steps. And those screw everything up because the rate law of the individual steps determines the overall rate law, not the overall equation. But we can use the mechanism to find the rate law if you know the steps. So what we need to first find is what reaction mechanisms lead to the rate laws so that they're consistent with what we observe experimentally. This is actually a way we can see if our multi-step mechanism is reasonable. If the multi-step mechanism gives us the rate law we expect, it's reasonable. So if we know that a reaction is elementary, we know its rate law. And again, we only know if a reaction is elementary if we are told so. We can write the rate law of an elementary reaction based directly on its molecularity. So if it's just one molecule, unimolecular, that means it'll be first order. Bimolecular would look like that. So again, the rate law for all elementary reactions follows directly from the molecularity. You can really just write down what the reactants are, and now their orders are their coefficients. It's as simple as that. But again, if it's a balanced equation, you cannot tell if it's elementary or multi-step. You got to be told if something is elementary. So we're going to assume that the following reaction is elementary, and from that we'll predict the rate law. So if that is the elementary reaction, so the rate law should be this. I see hydrogen, I see bromine, so I write hydrogen and bromine. They each have a coefficient of 1, so they each have an order or exponent of 1. Very straightforward. Now as a note, experiments show that the rate law for this reaction is actually this. So what does that tell us? Because the experimental rate law does not match the predicted rate law, that tells me the reaction is actually multi-step. So if it's multi-step, how do we determine what the rate law for the overall equation is? We use something called a rate determining step. Now again, most reactions occur in at least 2 elementary steps, and each of those steps will have their own rate constant, own activation energy, own rate law, everything. But one step will be much slower than the others, and I'll give you a hint. It's the one with the higher activation energy. Anyway, one is much slower than the other. So what we find is that the overall rate of the reaction cannot be faster than the slowest. The slow step determines the rate. It's like if you have to do two things to do something, the slow thing determines how long it takes. For instance, if you want to get in your car and drive to a city 3 hours away, you really have two steps. Get in your car and then drive. They get in the car's likely the fast step. The drive for a few hours is the slow step. The driving determines how long it takes. So we call the slow step the rate determining step or the rate limiting step. Unless you are told that a particular step has a high activation energy, you'll be told what the slow step is. There is no way to identify this just by looking at it. Now again, why do we worry about all of this? Because again, the slow step limits the whole reaction. The slowest step limits the overall rate. In other words, the rate determining step determines the rate law as well. Kind of. So here we have an energy diagram with two steps. We see one step here, and we see one step here. Because this one has a lower activation energy, it's the faster step. Because this one has the higher activation energy, it's the slower step, therefore is the rate determining step. So, if your mechanism has a slow initial step, so let's look at this reaction here. Below 225 degrees, we find experimentally that the rate law for the reaction is second order to NO2, zero order CO. So the rate law would be this. We know this experimentally. Here is a possible two-step mechanism. Step 1, step 2. Notice I labeled that first one slow, and that's what you're going to see, is that slow first step. So, overall, and we can look at this, like the NO3 gets canceled, so we're canceling out, and NO2 there gets canceled, so it does add up to the right thing. But if we want to see if this is reasonable, we have to look at the slow step. So again, the NO3 is slow, the first step is slow. That means the first step is the rate determining step, so the overall rate of the equation equals the rate of step 1. That means the rate law of the overall reaction equals the rate law of step 1. So step 1 is bimolecular, has a rate law of that. The 2 there is because there's 2 of them, which matches the rate law that we find experimentally. So that is a reasonable mechanism. So let's do another. So we have decomposition. This is the 2 steps. Again, the first step is labeled slow. We're going to write the equation for the overall reaction and write the rate law for the overall reaction. So equation first, so here's them again. So looking at this, I could go, okay, I see that O is produced, O is used up. That looks like it. Looks like there's 2 and 2 O's. So the overall reaction would look like that. Also 2 nitrogens, it looks like. So there's the overall equation. Now to find the rate law for that, since it's just the rate law of the slowest step, we just write the rate law for step 1, which is that. That's our rate law. That's it. Now things get muddier when you have a fast initial step. And the reason for that is that the first step is fast. It's not the rate determining step, which means the rate determining step, the second step, has an intermediate in it. And you can't have an intermediate in your rate law. So here's a possible reaction for this mechanism. Now notice when we do this, if the first step is fast, we assume that there's equilibrium. And so there's actually 2 kind of rate laws here. There's the rate for the first forward reaction and the rate for the reverse. But there's that slow step there. There's step 2, the slow step. And I talk about that, the forward and reverse, it's an equilibrium. Because step 2 is the slow step, it is the rate determining step, so that's what the rate law for the rate determining step should be. Problem, NOBr2 is an intermediate. We cannot use it in our rate law, so I got to get rid of it. So how do we do this? We make some assumptions and we do some math. So we can express the concentration of the NOBr2 in terms of the concentration of the starting reactants, NO and Br2. So what we're going to do is we're going to assume that NOBr2 is unstable. And there's two ways that NOBr2 can be used. It can react with the NO to form NOBr, like it does in the second step, or it actually falls apart. It breaks apart back into NO and Br2. If you remember, that was the first step of NO and Br2 forming NOBr. So it's going to fall apart back into the reactants. And again, the reason for that is step 1 is fast, so it'll happen quickly. It'll happen a lot. So there's step 1 again. So that NOBr is going to fall apart back into NO and Br2. Blah, blah, blah. So that's what we see. So I can actually set the rates equal to each other because it's at equilibrium. The rates are the same. So this is just the forward reaction and the reverse. Solving for NOBr2, I get this. Now notice this chunk here. Rate constant for one direction, the forward, over the rate constant for the reverse. But it's a constant over a constant. And if I divide a constant by a constant, what do I get? You get a new constant. The actual 1 and -1 doesn't matter. It's just a constant. So we can now plug that into the rate law because we're saying NOBr2 equals this mess there. So there's that. That's what the rate law would be for step 2. Instead of NOBr2, I plug in this mess here. Now notice I have this whole mess of K's. It's a constant times a constant over a constant, which means it's a constant. The actual values don't matter. It's just all one messy constant. And then I have 2 of the NOs, so NO squared. So that gives me the rate law. This is the rate law for the overall. So in general, what we can do, here's what I did, really, is I took the intermediate, took the first equation, the fast step, and solved it for the intermediate. Then I plugged that back into the rate law. Last slide, we're done. Catalysts, how do catalysts look? Catalysts will lower the activation energy by providing a different mechanism. It actually changes the mechanism. Now we know, we're always told the catalysts aren't used up in the reaction and they're not shown in the final equation. That's because they are consumed in the first step. That means they are a reactant in the first step and a product in the second. So they're still going to be canceled out for the overall equation, but they don't show up in the overall. Think of them kind of like the opposite of an intermediate. Intermediates are made in the first step and used in a later. These are used in the first and made in a later. And that's it. You're done. You're good. Run away.